Hello and welcome to our physical sciences session. My name is Themba Ncube. Today we are focusing our attention on understanding molar concentration of solutions. So when we talk of solutions, something immediately comes to mind. We think of substances dissolved in some form of a medium or a solvent. So we want to actually understand exactly what happens when a substance dissolves, and then exactly how then do we actually measure or quantify concentration of a solution. Okay, right. So in as far as the bigger concept of quantitative aspects of chemical change, we know that the mole is the SI unit of quantity of matter. Okay, so the mole is just a number which is also based on the mass of sample. And now if we talk concentration, we are actually asking ourselves as to how much of a substance is dissolved in a certain amount of solution, and then at the end of the day we are able to say, okay, this is the concentration. So our focus for today would be on concentration of solutions. Okay, right. So what's the thought that's going to guide our discussion for today? We would ask ourselves critical questions such as, what happens when a substance dissolves in water, and why water in particular? We are very much aware that many of the reactions that occur in real life, they actually take place in aqueous solutions. So the reason why we focus on water, because water is the most common solvent around us. So our understanding of the amount of substance dissolved in a given amount of solvent is very important in as far as the quantitative aspects of chemical change. Okay, now the second question says, what happens when a concentrated solution is diluted? Now, when it comes to dilution, you immediately think of your drink, at home, the sweetened drink. If you pour water to it, what happens to its concentration? Are we adding more water so that the concentration gets higher or lower? These are some of the things that we want to actually discover by the end of this session, right? Okay, so what are some of the key words that we will be using once too often in our discussion? The first term is concentration. The symbol is C, small letter C, okay? So when we talk of concentration, we're talking about solutions, okay? So we need to qualify the word concentration, because again, when we say concentration, and just end it like that, the context may be different. Here we are focusing our attention on concentration of an aqueous solution or a solution. All right, okay, the term solution, we have already used that once too often, from the beginning of our session. And also the term solute, as in a substance. A solute is the substance that actually dissolves, okay? So we'll use this term quite a lot. And then a solvent is the substance that actually dissolves, in which the solute dissolves, okay? And then we know something about a homogeneous mixture. We know that, matter can either be pure or impure substance. So we know that pure substances, in terms of classification, are your elements and compounds. But then if you talk of impure substances, we're talking about mixtures. And there are two broad categories of mixtures: homogeneous and heterogeneous. But our focus is on homogeneous solutions in this case, in the context of, solutions. Right. Now let's look at, the idea, or the big idea of the molar concentration of a solution. Okay. So when a solute, which is a substance, dissolves completely in a solvent, a homogeneous mixture is formed. Okay. So a homogeneous mixture is formed as a result of a solute dissolving in a solvent. Now, the word dissolve does not necessarily mean react. We need to be very careful. So when a substance dissolves in water, we are saying water is the substance in which this solute is actually placed, and these particles that make up the solute are surrounded by water molecules. That's a simplest way of describing what dissolving is all about. Okay, but remember, a homogeneous mixture is formed. So a solution is a mixture; it's not a new substance. Okay. So a solution is a homogeneous mixture. That's the main point that we want to drive home. And then also, a solute is a substance that dissolves in a solvent, Water is the most common one. So in any case, when you have a solute and a solvent together, you form a homogeneous mixture. So that's the mixture that is formed, okay? So this mixture would refer to it as a solution, all right? Okay, and then most reactions in real life, they take place in aqueous solutions. It means there must be a solvent. So this reaction takes place in the midst of a solvent. So there must be a solvent to allow these particles to react with each other to form new substances in any form of a chemical change. Okay, so where does this take us? The stoichiometric calculations, very, very important. But we need to also understand that we need to first understand what exactly dissolving entails. And then when we talk stoichiometric calculation, it means then we are able to apply what we know. So it's not just about the calculation, but it's the science behind those numbers. So immediately, the point we start doing calculation, we need to ask ourselves, why do we do the calculations that we do in stoichiometry? So that understanding is something that we need to be very comfortable with, okay? So in these stoichiometric calculations involving solution, it remains key to understand what quantity of the solute is dissolved in a solvent. So this is with respect to solutions. And also, concentration of a solution is actually it's an indication of the quantity of solute dissolved per unit volume of solution. Let's look at in more detail what concentration is all about. In terms of definition, we are saying that concentration of a solution is defined as the number of moles, okay, or the moles, because the mole is actually a number, okay? So it's the moles of substance per unit volume of solution. So it's the moles of substance per unit volume of solution. So if you are to put that mathematically, we are saying that the amount of, actually the concentration is equals to the amount of dissolved substance in moles, okay? Because quantity of substance or amount is actually the mole, okay? Then the volume, SI unit, is the cubic decimeter, okay? A decimeter is actually equal to 1 liter. So we are saying that 1 liter, okay, is equals to 1 cubic decimeter. Okay, so the decimeter is the metric equivalent of a liter. So a liter is the same as a cubic decimeter. So mathematically, in your data sheet, this is the formula you need to familiarize yourself with in as far as concentration is concerned. So C is concentration, then this is moles, okay? Okay, that's the moles of substance, okay? Then that's the volume in cubic decimeters. So the SI unit of concentration of any solution will be in mole per cubic decimeter, okay? So that's the SI unit, right? So remember, the mole is the number, which is the amount of substance or solute that is present per unit volume of solution. Hence, we are saying that the SI unit of concentration is mole per cubic decimeter, right? Hey, that's what we want to understand. And furthermore, what is it that we know already? We know that the mole, which is the SI unit of amount of matter, which is a number, is actually mass divided by the molar mass of substance. So if we combine the concentration formula and the mole formula, because this is about the mole, it gives us this version. When do we use this equation? We shall establish as we go along that if we've got a mass of sample and the volume of solution, we are able to determine its concentration. Right. Now let's focus our attention on some of the implications in as far as the SI units are concerned. There are multiple types of units for measurement, and at some point or the other, it may be very necessary for us to actually carry out conversions, okay, before we do any stoichiometric calculations, all right? Now, some of the common units that we use in stoichiometry are the cubic decimeters, cubic centimeters rather, but we know that if we're saying that concentration of a solution is moles per unit volume of solution, now we are saying that the SI unit of concentration is mole per cubic decimeter, right? So volume must be in cubic decimeters. Now it means even mass has to be changed to the moles. Okay, we ask ourselves, given a mass of sample, how many moles of a substance or the solute is present in that mass, and then volume must be in cubic decimeters because that's the SI unit of volume, right? So if we have, let's say for argument's sake, cubic centimeters, cubic millimeters, okay, in a cubic centimeter, there is actually 1,000 cubic milliliters, okay? And then if we want to change, say for argument's sake, cubic centimeters, okay, to cubic decimeters, right? Okay, we know that from cubic centimeters to cubic decimeters, we divide by 1,000. If we divide by 1,000, it's like we're multiplying by 10 exponent negative 3, okay? And then if we want to move from cubic decimeters back to cubic centimeters, we multiply by 1,000, which is 10 exponent 3. So these are some of the practical examples. We may also have cubic meters. We know a cubic meter has got 1,000 cubic decimeters. And the most important practical one is actually the liter. And we are very much aware at this point in time, or that we need to remind ourselves that a cubic decimeter is the same as a liter. So when we say a liter, we're talking about 1 liter, which is equals to 1 cubic decimeter. So that's as far as, you know, understanding the concept of concentration, which the big idea around it in terms of the definition is that, you know, when we talk of a concentration of a solution, we're talking about the moles of solute per unit volume of solution. The mole represents the number of particles of that solute which is present per unit volume of solution. No, we're not saying water, but we're saying solution because it's a homogeneous mixture. In the next segment, we'll try and look at a simulation and try to discover some of the very exciting, you know, aspects of the concept of concentration in as far as diluting, you know, what happens if you add a lot of solute, you know, to a liquid, what happens to it in terms of the concentration, and try and discover some of the, you know, exciting, you know, facts about concentration of solution. For now, let's take a short breather. Welcome back to our second segment. We're still looking at concentration of solutions, and we are saying that concentration as a quantity, it gives us an indication of the amount of solid. Then when we talk of the amount of solid, we are talking about the moles of that substance per unit volume of solution. And we said that earlier on that concentration in terms of SI unit is measured in moles per cubic decimeter. So when doing stoichiometric calculations, there may be times that it will be necessary for us to actually do the necessary, you know, conversions in terms of the SI unit. Right, having said that, let's look at the thought once again, just to take us, you know, to the next stage of our discussion. It says here, what happens when a substance dissolves in water? So the understanding is that when we talk of a solution, we immediately want to think of a homogeneous mixture. So if a substance is a homogeneous mixture, it means it is an impure substance. And then within this solution, there are particles of the solute surrounded by particles of the solvent. And these two can be separated, you know, by physical means. That's what we know already, okay? So when a substance or a solute dissolves in water, what exactly happens is that these particles of the solute are surrounded by water molecules. And the context in which, you know, solutions are very important is in terms of the reactions that take place in aqueous solutions, okay? So most reactions in real life, they take place in a medium whereby these substances are surrounded by water molecules. Hence we talk of, you know, reactions in aqueous solutions. But for today, we just want to focus on concentration of these solutions, right? So we have an idea of what happens when a substance is dissolving. So dissolving is not necessarily a chemical reaction, okay? Right, so, and then the second thought is, what happens when a concentrated solution is diluted, right? Now, actually, we can think of it in terms of, real life. If you've got a concentrated, juice, which has got a very high concentration, what does high concentration mean to us? It says that there is a high number of moles of the solid per unit volume of solution. So when we dilute, what exactly are we doing? We are adding more solvent into this substance, and then we asking ourselves a question that says, what happens to the concentration? Does it increase, decrease, or remain the same? We shall try and establish that as we carry out a simulation that will resemble the real life scenario of what happens when you dilute any concentrated substance, okay? And then the third question says, how is concentration of a substance affected by amount of solute and volume of solvent? So there are two quantities that contribute to the concentration of a solution. One is the moles of the solute, and secondly, it is the volume of solution. Okay, hence we talk about the moles of solute per unit volume of solution. So we want to answer these questions by the end of this session, right? And then interpreting a known concentration of a solution. Let's say we have a concentration, let's say for argument's sake, C is equals to 1 mole, okay, per cubic decimeter, right? What does this mean when we say a substance has a concentration, or a solution has a concentration of 1 mole per cubic decimeter? Now, let's break this down. Okay, let's say for argument's sake, we've got 1 mole of hydrochloric acid, okay, in 1 cubic decimeter. Now, what does this mean? It says concentration is equals to number, which is the moles, okay, divided by unit volume. So if we have got a mole divided by a unit volume, then we actually get 1 mole per cubic decimeter, right? That's what we get, okay? So what does 1 mole per cubic decimeter of solution tell us? It tells us that there is 1 mole of the solute per unit volume of solution, okay? This is the unit volume of solution, which is 1 cubic decimeter, okay? Now, on the other hand, if we have got double the concentration, we are saying 2 moles per cubic decimeter. Let's take a different substance for argument's sake. Let's say sodium hydroxide. If the concentration of sodium hydroxide, for argument's sake, is equals to 2 moles per cubic decimeter, what does this mean? It means that there is 2 mole of sodium hydroxide per every unit volume of this solution. Hence, the concentration is 2 mole per cubic decimeter. And then on the other hand, if, say, for argument's sake, we've got sulfuric acid, okay, then the concentration is 6 moles per cubic decimeter. What does this exactly mean? If, say, for argument's sake, we've got 1.5 moles of sulfuric acid per, 250 cubic decimeters, okay? And then we want to understand what is the actual the concentration of this solution, okay? We are saying that, for argument's sake, let's say this is 250, okay, cubic centimeters. I just wanted to focus our attention on the conversion there, okay? So what do we have? We've got 1,5. So now concentration is number of moles over volume, or moles over volume. In this case, is not 0,15 moles. Okay, actually it's 1,5 moles divided by 250 cubic centimeters. Okay, I just wanted to focus on the conversion there. So 250 is actually 250 multiplied by 10 exponent minus 3, which is the same as dividing by 1,000. So this is like C is equals to 1,5 divided by 0,25. Okay, this is what gives us 6 mole per cubic decimeter. So what does this mean? It means per unit volume of that solution, there is 6 moles of the solute. That's the interpretation, right? Okay, now let's focus our attention on measuring the concentration of a solution. We'll draw our attention to a simulation that's going to give us an idea as to how we actually do that. So we'll start with a simple example, okay? Let's remove the water there, okay? So here is an empty container. What we're going to add in this container, let's say we add some volume, half a liter, okay? Right, so if it's half a liter, we have to reduce that to half a liter. So we open the tap, okay? So suppose we've got that half a liter there, okay? So if that's the volume of solvent, okay? That's half a liter, and immediately you have half a liter. What do you have? It's like 500, cubic decimeters, okay? Right, so we are saying that let's add, let's say for argument's sake, a certain amount of the drink mix, okay? Pay attention, we are adding the solid particles. You realize that immediately we start adding the drink mix into the water. What happens? It dissolves. You can notice the color change there. So we don't know how much we have added from that container, but we are able to measure how much of the drink mix is actually in this solution. So we'll take our concentration meter and put it there, okay? I just want also to realize that if we keep on adding the drink mix, what is happening to the concentration? The concentration is getting higher and higher. What does that mean? As we add more solid particles into the solution, what is happening? The moles of the solid, it increases. So if the volume of solution stays the same and we keep on adding more solid particles, what happens? The concentration is going to increase. Okay, this is what we can actually change that and use actual substances. Let's say, for argument's sake, we use copper sulfate. Okay, there is copper sulfate. All right. Then we have, let's say, a certain amount of water in that. Let's use a liter for now and see what happens. Okay, so that's 1 liter. Okay, so this is 1 cubic decimeter if you want to think of it. Now, if we're going to add copper sulfate, what's going to happen? It will dissolve completely in water. Okay. Now, what has happened here? You can see as we add more and more solid particles into that solution, the concentration increases. What does that tell us? More particles of the solid are surrounded by water molecules, and as we keep on adding more, the concentration will also increase. And we are able, after that, to actually determine the amount of copper sulfate that was added into the solution, because we have the concentration. So that's the big idea in as far as concentration of a solution is concerned. Okay, so that's how, if we have the volume of water, because we know that C is equals to N over V. So if we have got the volume of water, okay, this is the volume of the solution in cubic decimeter. So that's our volume, right? And then that's the moles. Okay, we can get this from the mass over molar mass of substance. So take note of that. So the number of the moles is actually the number of particles of the solid. So the V then represents the volume of the actual solution. Okay, right. Okay, now if we are to move further, we want to look at, using the simulation once again, how we prepare what is called a standard solution. Now let's ask ourselves, first of all, this is a very important term. What is a standard solution? It's a solution whose concentration is known. So any solution that we know its concentration, we can describe that solution as a standard solution. So in a nutshell, what is a standard solution? It's a solution whose concentration is known exactly. We know its magnitude of concentration. It's X moles per cubic decimeter. That's what it means, okay? Now, suppose, for argument's sake, we want to prepare this volume. This is the volume, 250 cubic centimeters, okay? That's the volume of solution, okay? Cubic centimeters of this concentration, 0.1 mole per cubic decimeter of sodium chloride. We want to know the mass of the solid to be dissolved so that we get that concentration of that volume. So this is the concentration, okay? So if we ask ourselves, do we know the concentration of the solution? Yes. Then if we know the concentration, which is 0.1 moles per cubic decimeter, then it simply means that solution can be described as a standard solution, right? So let's go through the steps. First of all, we have the volume. The volume is actually 250 cubic centimeters, but do we need to convert this? Yes. So 250, it's like 250 divided by 1,000, okay? Because in a cubic decimeter, there are 1,000 cubic centimeters. So this gives us 0.25 cubic decimeters, all right? This is like a quarter of a liter or a quarter of a cubic decimeter. The next thing in terms of stoichiometry, we want to know the molar mass of sodium chloride. So the molar mass of sodium chloride from the periodic table of elements, we know that sodium is 23 grams per mole plus chlorine, which is 35.5, okay? So the molar mass of sodium chloride becomes 58.5 grams per mole, okay? 58.5 grams per mole, all right? Okay, and then we want to know what is the mass of the solute which is dissolved in that particular solution. So what do we know? We know that concentration is equals to mass over molar mass times volume. We are immediately reminded of this version of the formula, okay? Now, we are looking for the mass of sodium chloride that is actually dissolved, that is in the solution, if the volume of the solution is also given. So we have the concentration, we know the molar mass, we know the volume, we are able then to determine the actual mass of the solute that was dissolved. So we can do this via a way of a simulation just to show exactly what happens, okay? So if we go to our simulation, let's change that to sodium chloride because that's our substance, and then the volume of water that we must, of the solution, the total solution must be a quarter. So a quarter is like 250 cubic centimeters, okay? So that's 200. So the 250 is actually between 200 and 300. So that is it. So if we add the sodium chloride, okay, it will dissolve in that. So we want this solution to have a concentration of 0.1. Already, clearly, we've added a lot of the solute there. So if we can maybe just reset that so that we get an idea of exactly what happens in practice when we will have some water, which is 250. With 250 is exactly in between 200 and 300 cubic centimeters, okay? So we have overshot that. So that's our idea of 250 cubic centimeters. You can tell it's the half of half a liter, which is a quarter of a cubic decimeter. So if there is no solute here. That's why the concentration value reads 0.0 moles per cubic decimeter. Remember, a liter is a cubic decimeter. So this is another way of saying moles per cubic decimeter. So our concentration, if we can quickly go back to the slide just to confirm, the concentration of our solution must be, if we can quickly go back and verify that, must be 0.1 moles per cubic decimeter, right? Should be 0.1 moles per cubic decimeter, right? So let's take note, pay attention to the change. As you can see, already that is 0.039. So we need 0.1. So we must add more of the particles of the solute, okay? So that actually we have overshot. So as we keep on adding, you can see the value of concentration is also increasing because the volume of the solution stays the same. We're actually adding more particles of the solute, okay? So that's exactly, we're just trying to resemble what happens in practice when you determine, the concentration of a solution, right? So we have the concentration, which is, if we do our substitution, 0.1, okay, is equals to mass. Remember, we want to determine the mass of the solute, which is the sodium chloride, okay? This is divided by, molar mass is 58.5. multiplied by the volume 0.25, okay? So the mass of dissolved solid, if we can quickly verify that by way of calculation, right? James? Okay, I lost the calculator, sorry. Yeah. Okay, sorry. 2 minutes, okay. All right, I'll minimize it. Yeah. Yeah. Okay, we have got 2 minutes. Okay. Yeah, I'm fine. No. Okay, so just to verify, to get the actual value of the mass of the solid that has been, okay, sorry. Okay, now just to calculate the actual mass of the solid in that solution, we can go to our calculator, okay? So what do we have here? We've got the concentration, the volume, and then the molar mass. So the mass is actually a product of those three, which is 0,1 concentration multiplied by 58.5, which is the molar mass of sodium chloride, multiplied by the volume converted to cubic decimeters, 0.25, okay, 0.25. So what mass was dissolved is 1.46, okay, so that's 1.46 grams of sodium chloride was dissolved, okay. Now let's look at a situation in terms of what happens to a solution if we keep adding more solid to it. Remember, the solid must actually dissolve in the, in the solvent. Now, this is we're using a drink mix, which is very popular. You can immediately realize that the particles are no longer dissolving. I think this is a common observation. If you add a lot of sugar, to the tea, at the end of the day, the sugar particles do not dissolve anymore because the solution has become saturated. That's what it means. Okay. So going back to our simulation and just to understand, okay, what happens to the concentration of a solution when we keep adding more water? If we go back to our concentrated, saturated solution, let's add more water to it. Take note of the concentration reading there. So if we add more water to it, what's happening to the concentration is getting lesser and lesser because the volume of solution is getting bigger and bigger. So if we add more water, the concentration decreases because it's for the same number of moles of the solid, okay? Right, so what does this mean in terms of our understanding or our discovery? The ratio of the moles of solid dissolved per unit of solution is an indication of concentration. This actually speaks to the equation C is equals to N over V. Okay, furthermore, a solution of a higher concentration may sometimes have a darker color. This is, what we observe. If we added a lot of, drink mix, the color was so strong, and the less concentrated one was comparatively lighter. Okay, so this is in terms of observation. And then again, adding more solid into a solution of constant volume. Remember, we didn't change the volume in the other case. It will result in a solution becoming saturated. So these are some of the important discoveries that we have made in terms of solutions of concentrations of solution. Now, after the short break, we'll try and look at a situation which involves the actual stoichiometric calculations. Let's take a short break for now. Welcome back to our third and final segment. We're still looking at concentration of solution, but now we want to focus our attention on the actual stoichiometric calculations and maybe discuss a way in which we approach these questions and what are some of the very important things that we need to pay careful attention to. Right, so without any waste of time, we have a scenario here based on calculating concentration of a solution. We are given mass of sodium nitrate. So the substance is sodium nitrate. The mass is 4.25 grams. It is dissolved completely. So this, the dissolving is actually complete in this volume of water, which is 250 cubic decimeters. And now we want to calculate the concentration of the solution. Okay, now first things first, we know that concentration is equals to moles per unit volume. But we ask ourselves, in the 4.25 grams of sodium nitrate, how many moles are present? We know that number of moles of sodium nitrate, okay, moles of sodium nitrate is equals to mass of sample divided by the molar mass, okay? So what's the mass of the sample? 4.25, okay, grams, right? Divided by the molar mass of sodium nitrate, which you go to the periodic table, it will give you 85 grams per mole, right? So the number of moles, or the moles, is actually, we can just quickly do that by way of calculation. What do we have? We've got 4.25, right? 4.25 divided by 85, okay? Now, this tells us that we've got 0.05 moles of sodium nitrate. So it's 0.05, right? 0.05 mole, okay? Now, then if that's the case, then we know that C is equals to 0.05 divided by the volume of solution. The resulting solution will be 250. So this is like 250 times 10 exponent negative 3. Why 10 negative exponent 3? Because we know that 1 cubic decimeter is actually equals to 1,000, okay, cubic centimeters, right? So to move from cubic centimeters to decimeters, we divide by 1,000, okay? So if we go to our calculator, this will give us, if we want to find the concentration, we ask ourselves how many moles of the substance, 0.05, divided by the concentration, so the volume of the solution, which is 250 times 10 exponent negative 3, right? So this will give us the concentration of the solution. So this solution is 0.2 moles, has a concentration of 0.2 moles per cubic decimeter, okay? 0.2 mole per cubic decimeter. So this is what we are required. So what did we do? Just to go over the steps. Given the mass of the sample of the solid, we asked ourselves, in that sample, how many moles of that substance are present, okay? Then we used the formula, moles is equals to mass over molar mass. Once we got the moles of the sample, we divided that by the volume, because concentration is actually the moles of substance per unit volume of solution. Then it's actually a multi-step problem, or you can do it directly using C is equals to M divided by MV. We have seen that in the previous example, okay? Now, let's move forward. It says here, calculate the mass of copper 2 sulfate, okay, needed to make 650 cubic centimeters of this solution, which is 0.5 moles per cubic decimeter. That's the concentration. So what do we have? We've got the volume, right? So that's the volume, okay? Now this volume is given in cubic centimeters. We also have the concentration, right? We have the concentration. Take note, in this case, concentration is given, but we're looking for mass, right? So it's like we're working backwards now. But this is hydrated copper 2 sulfate, okay? Because it has got water of crystallization. So it would be typically a blue, solid substance at room temperature, right? So the question here, we want to determine the mass, okay? What do we know? We know that concentration is equals to mass over molar mass times volume, okay? So we have the concentration, but also we need to know the molar mass of this substance. So if we go to our periodic table, we know that the molar mass, we'll get the molar mass of hydrated copper 2 sulfate, okay, the formula CuSO4, and then 5 moles of water of crystallization. So this is the water of crystallization. So if you carry out the calculations from the periodic table, you get a value like 250, okay, grams per mole, right? So the question wants us to determine the mass, but the volume that is given in this case, V is equals to 650, okay, times 10 exponent minus 3 cubic decimeters, right? So that's the volume. Now, the question wants us to determine the mass, okay? So if we want the mass, we would say, okay, the concentration we have is 0.5, okay, is equals to the unknown mass, right? Okay, then the molar mass is 250 grams per mole, okay? The volume is 650 times 10 exponent minus 3. This is like 0.65. Then our mass is the product of those three. If you do not have to carry out the subject of the formula, just copy the equation as it is and then do the necessary substitution. Immediately after that, you can isolate the unknown. Then if we go to the calculator just to get that value, now this is the maths part, okay? It says here 0.5, that's the concentration, okay? Multiplied by the molar mass, which is 250, okay? Multiplied by the volume in cubic decimeters, which is 650 times 10 exponent negative 3, right? What does this give us? It gives us a mass of 81.25. So in other words, 81.25 grams of the copper sulfate must be dissolved to form a solution of a concentration of 0.5. So we can work either way. So the formula for calculating concentration, C is equals to M over MV, is not just for concentration. It can be mass, it can be volume of solution, it can be the molar mass of the solute given the concentration. So in most cases, you'll only have one unknown, and there will be a way in which you can determine the other variables. Okay, right. Now, having said that, let's move on to the next, the third and final example that we want to carry out. We also given here a mass of aluminium chloride, which is 6.675 grams of aluminium chloride, which is dissolved in water, and the final volume of the solution is 500 cubic decimeters, okay? So we want to determine the concentration of the solution. First things first here, we need to understand the solute that it's aluminium chloride, okay? From our chemical formulae, we need to be able to determine the correct formula of the solute so that we are able to use the periodic table to get the molar mass. So aluminium as a transition metal, it occurs as Al3 plus cation, and then we also have Cl minus, which is the N ion. So the resulting formula of this ionic substance is actually AlCl3, right? Okay, so we can also then from this moment also already determine the molar mass of it if we know the formula. Okay, so the molar mass of aluminium chloride is 133.5. That's what you get from the periodic table, okay? Grams per mole, right? This is what we need, okay? So we moved from the correct formula to the molar mass. We are given the volume and the mass. We are determining the concentration, right? So what do we know? We know that concentration of aluminium chloride, for argument's sake, okay, that's the formula, is equals to the mass of sample divided by the molar mass multiplied by the volume. Okay, so this is the formula. So each time you are given, you're looking for something, the formula is always given on the data sheet. There is no need whatsoever for you to try and make this and change the subject, because in the process, things might go wrong, you know, and then after that, the resulting calculations will also be incorrect. So to avoid that, copy the formula as it is given, do the necessary substitution, and then isolate the unknown. Now, we are saying we are looking for the concentration of the chloride, okay, aluminium chloride, right, which is equals to, we have the mass is given 6.675, right? So 6,675 grams divided by the molar mass. We've understood that the molar mass is 133,5 grams. Okay, so it's 133,5. Right, this comes from the correct molecular formula. Okay, multiplied by the volume, and the volume we were told that is half a liter, which is 500 cubic centimeters. 500 cubic centimeters is the same as 0.5 cubic decimeters. Okay, so whatever concentration we'll get from this calculation will actually be in moles per cubic decimeter. So our concentration of the aluminum chloride in this case becomes, okay, then we can evaluate that by way of calculation. So this is, okay, if we can quickly punch that, 6,675, which is this mass of the sample, 6,675 divided by the product of the molar mass and the volume, which is 133,5 multiplied by 0.5, right? Okay, this gives us a concentration of 0.1 moles per cubic decimeter, okay? 0.1 mole per cubic decimeter, okay? So that's the concentration of the solution, okay? Now, the follow-up question says, if this dissolves completely, the aluminum hydroxide dissolves completely, what is the concentration of aluminum chloride ions in the solution? Okay, this is an interesting question because we know that aluminum chloride is actually an ionic substance. Okay, so in that solution we have got Al 3 plus, okay, and then plus Cl minus. Okay, but if we balance this, this will be 3, okay, cations of 3 moles of the chloride ions. So the stoichiometric ratio once again is 1:3. So if this completely dissociates, it will have a concentration of 0.1 mole per cubic decimeter. Okay, it will give us 0.1 mole per cubic decimeter. Okay, and then this will be 3 times the number of moles. So the concentration will be also 3 times bigger, which is 0.3 moles per cubic decimeter, right, of the chloride. So still the ratio remains 1:1:3, right? So in a nutshell, in closing, what are we saying? The mole is the SI unit of quantity of matter. We continue to maintain that, okay? And also the unit of molar concentration is moles per cubic decimeter, which gives us the reason for us to carry out the conversions in terms of the units. And also, we've also discovered that what is so important about a standard solution is that the concentration of a standard solution is known, right? And furthermore, how does this fit in terms of stoichiometry? Everything is about the mole, which is the SI unit of quantity of matter. And among concentration, we talk volume, we talk moles, which is a number, we talk masses of substances, which took us to the formula C is equals to M/mv, right? So that's as far as, concentration and the stoichiometric calculations around concentrations of solutions are concerned. Hopefully this makes a lot of sense, and to some extent it shows how all these small pieces of the puzzle come together. Hopefully it made a lot of sense, and we've discovered some of the very exciting things about concentrations of solutions. From myself, Themba Ncube, cheers and bye-bye for now.